Okay, so let me open up the notes and we'll continue with this. So uno momento. Okay, arc links, yes. Okay, switch to writing mode. Window capture. Oh, okay, wait. My size of my screen is messed up. Or my size of my video is messed up. That's a better way to put it. I need to make myself smaller. But not that big. Okay, smaller. There we go. Yes. Okay, cool. Okay, so last class, where we left off, was we were talking about polar coordinates, right? So we were talking about r and theta. And this example that we just did is sort of a good review of that, the equations that relate them. And then we were talking about regions bounded by polar curves. So the big thing that I was talking about was, let's distinguish these regions and areas if we're talking about rectangular coordinates or if we're talking about polar coordinates. So on the right here, I have my rectangular coordinates. So notice when we're doing like a limit, we're going to integrate from A to B, right? You can see it, it's like right beneath me, right? Like A is like, oh, my hand can't quite go that far, but like the A is like here, and then like the B is right below this hand, right? You integrate from A to B. So your bounds, those are vertical lines, and you use those vertical lines to make rectangles parallel to it to estimate the area. But that's different than the polar case, because in the polar case, our function, our radius is determined by theta. It's parameterized by theta. And if you think of theta, that's angles, which are like these like radii, right, that come out, right? If you think of like a radius, it has a constant angle, right? Which is why you get, let me sort of like draw it. You get, oops, these, oh, let's just, if here's your axis, you draw out a little thing like this, like theta equals pi over 4, or theta, oops, that's like completely wrong looking, but whatever. Theta equals pi over 3 or something. Okay, so those are sort of like the x equals a. You want to find area between like theta equals pi over 4 and theta equals 3, and then you have your f of theta that looks like this. You're interested in this region. Okay, and just like how on the rectangular side, you break up x equals a to x equals b into equal size delta x's, you do the same thing on the polar side where you break up theta equals alpha to theta equals beta in delta thetas. So you get these angle like little chunks that are equally spaced. I think I was calling them pizza slices the other day. Right, does everyone see the little pizza slices in the polar graph? They're the equivalent of the rectangular pieces to estimate the area. Okay, so is this sort of reminding everyone of what we did last time, hopefully? Okay, so we need to keep going. Okay, then I reminded you of how, right over here, right, your integral is defined in terms of the limit of the sum of the rectangles. We have formulas for delta x and we have formulas for xi to do all of that. What we're going to do today is figure out how to do that for polar coordinates or polar equations. Okay, so let's start off with a circle. Okay, so if you go back up to here, this stuff that we want to figure out, what do we call this? If this was a circle, what would we call this stuff right here, this pizza slice looking thing? It has a special name. You should have known it from like in trigonometry. What do we call that? So what do we call that stuff? Like if you look, not a conic section, something else. Do we happen to remember? Oops. Yeah, sector, thank you. Okay, so this is a sector. A sector is like that little slice of a thing. Okay, so in a sector, you usually have some angle, which we'll call theta, and you have a radius, and you can figure out the area of said sector. And it's actually not that hard to figure it out. So we're going to start off by saying that the area of the whole circle is pi r squared. Okay, the area of the whole circle is pi r squared. Now, this sector is only part of that. Okay, I want to type. The sector is part of the circle. And it is a particular percentage. And the percentage of the circle it is whatever theta over 2 pi is. Right, does that make sense? The bigger that theta is, oops, that's not 2 pi, that looks like 2r. It's supposed to be 2 pi. But does that make sense? Because 2 pi is the maximum size of the angle you can get in in a circle. However, the theta divided by 2 pi is like the percentage of the circle that the sector is. So you get this formula. You can say like, well, okay, the area now of the sector is the percentage of the area of the circle. Okay, the pi's cancel, and you get 1/2 theta r squared. So you might remember this formula from trigonometry. They gave you the sector area formula. It actually makes a lot of sense where it comes from. It's 1/2 of theta r squared because you just cancel those pi's, right? And you get whatever percentage of the circle that area is right there. Okay, making sense? Now we're going to use this. This is actually going to be really useful for us. You might be wondering, like, Professor, why do you give a shit about this formula? Well, let's draw a picture and you'll see why. Okay, so here is my axis. Actually, wait, I don't like this axis. I want a different looking one. I want one that looks like this. Oh yeah, sure. Like there? Okay, cool. We'll let it sit there for a moment. No problem. Okay. So, you've got your function r equals f of theta. And you want to find the area between theta equals alpha and theta equals beta. That's like your area between x equals a and x equals b. Okay, so remember how we took the region... we took from x equals a to x equals b, and we split it into equal parts, delta x, which was b minus a over n. Okay, so we're going to do the same thing here. We're going to take the between theta equals alpha and theta equals beta and split that into equal parts called delta theta, which is beta minus alpha over n. So for instance, let's just say we're going to split this into 3 equal parts. You would get a number right here, a number right here, and a number right here. This would be your theta 1. This would be your theta 2. This would be your theta 3. And they're each delta theta apart in terms of the amount that you rotate, right? You would rotate delta theta, you would rotate delta theta, and then you would rotate delta theta. Okay. Now, delta theta 1 is a number. And this, remember that r equals f of theta? So if you plug in theta 1 into f, that gives you the distance from the origin to right here. So the length of this is equal to f of theta 1. Okay, that's that radius right there. Sure. Okay, so f of theta, you take an angle, you plug it into, so if you take a theta and you plug it into f, it gives you a radius. That's what this tells you. So we have this number, theta 1. If you plug theta 1 into f, that will tell you the length of this line segment right here. Okay. Now this is the cool thing. How much rotation do we have in this little sector right here? I told you earlier how much angle is in each of those 3 sectors. We have our 3 sectors. How much angle was in each of them? Delta theta, thank you. So we can actually figure out the area of this sector using the sector area formula. The area of this sector is equal to 1/2 of theta. Well, the theta there is delta theta. And then you multiply by the length of the radius squared, and we know what the length of the radius squared is. It was f of theta 1 or theta I. So this sector right here has this as its area from the sector area formula. We split up the sectors into equal parts. That's why we know that the angle there is delta theta. And we have our theta 1 to figure out the radius. And boom. Now, if you want to find this total area, if you want to find the area between theta equals alpha and theta equals beta, what do you simply need to do? If you know the areas of each of those individual sectors. Cool, yeah. So in other words, you would get, we call this A1, right? Because that was the one for delta 1. You would simply do sigma I equals 1 to 3 of AI. Right? You would add up those 3, right? So generally, if you had n of them, you would just say sigma equals I equals 1 to n of AI. And we have a formula for each of these AIs. You would say sigma equals 1 to n of 1/2 delta theta f of theta I quantity squared. So this should look familiar to you. What would the equivalent of this be for rectangular coordinates? What would we call this stuff in rectangular coordinates? If we were adding up all the rectangles, the sigma of the rectangle, the area of the rectangles, what do we call that for the rectangular version? Do we remember? Starts with an R. Yeah, cool. So this is like the equivalent of a Riemann sum for polar coordinates. So whenever you see this, you should just think of, oh, that's just basically the freaking same thing as sigma equals I to n of f of xi delta x. Just it's rewritten in polar coordinates now. Now, what do you do to the Riemann sum to turn yourself into a definite integral? So what do you do to the Riemann sum to make a definite integral? Like, if I want this to be equal to integral AB f of x dx, what needs to happen? Excellent. So what are we going to have to do to our new Riemann sum up here, the sigma 1/2 delta theta f of theta I squared? Yeah, cool. Now, notice something. Do you see how when you take the limit of the Riemann sum, that f of x ends up as f of x over here? Okay. What does our delta x turn into? Over in the definite integral. Yeah, cool. So, when we take the limit of sigma I equals 1 to n of 1/2, and I'm going to write this in a slightly different order, f of theta I squared delta theta, I'm going to get an integral. Now, where did the a and the b come from in the definite integral? That came from x equals a and x equals b, right? So when this becomes a definite integral, what are my bounds of integration going to be? What's the equivalent of a and b for polar coordinates? Cool, yep. So I'm going to integrate from alpha to beta. Okay. The 1/2 f of theta I squared is just going to be rewritten in here as 1/2. And let's put the 1/2 out in front because we can move that. We'll just move the 1/2 out here. Right? Because you remember how you can factor out constants always? So we're going to get 1/2 f of theta quantity squared. And now what happens to delta theta? So what does my delta theta become? Yep. Boom. This is the formula for finding the area bounded by theta equals alpha and theta equals beta and f of theta. Just like how the other one is the area bounded by x equals a, x equals b, and f of x. Bam! So you can't just integrate f of theta is the weird thing here. You have to have f of theta squared in the formula. Okay, that was like a lot of work to show that, but it it should help you like understand why that's the case. Okay, so I'm going to give you a moment to like write stuff down, and then we're going to go forward. Alright, so let's do an example. So example, find the area outside of r equals 2 plus 2 sine theta and inside the circle r equals 6 sine theta. So it helps to draw these things. Okay, so let's draw the circle r equals sine theta first. Okay. So what do we know about this circle? It's going to have a radius of what? No. The one that I underlined in blue. What will the radius of this be? Actually, oddly enough, it will be 3. The diameter will be 6. We did an example like this the other day. So let's just start by plugging in theta equals 0. So if theta is 0, what do you get for r? Sine of 0 is 0. 6 times 0 is 0. So you get like a point like right here. Let's plug in theta equals pi over 2. What's sine of pi over 2? 1. Cool. And 6 times 1 is 6. So you actually get these 2 points, 0, 0, and 6, 0. And if you fill in the values between 0 and pi over 2, you get that part of the circle. And if you keep going, you get the rest of them. So you get that it's centered at 3, 0. A little surprising, but not too bad. Okay. So how would you do that? I would just recommend you go to Wolfram and graph it. So, or like do what I'm doing here, just start plugging in numbers. This thing has a weird shape. It's called a cardoid, or cardioid. So named because it looks sort of like a heart. If you were to graph it, it looks like sort of like this. 1, 2, 3, 4. So it hits right here at 4, 0. But it goes like this and like that. It looks sort of like the Airbnb sign. Let me redraw that. It looks sort of, I didn't do the greatest job doing it. There we go, that's a little better. But does everyone see how it looks like an upside down heart? That's where the name cardioid comes from. Like if you look at it upside down, it looks sort of like this. Okay, so what region are we interested in? What does it have to be? Yeah. Like, how do you describe it? Like, what's the description for it? It needs to be what? And what? Right. So, for instance, outside the cardioid could be out here, but that stuff is not inside the circle. So we're not going to get that stuff. So you only get this stuff right here. Right? Because that's the stuff that's inside the circle and outside the cardioid. Okay, now, you have some stuff you need to figure out. Remember, you're going to integrate from alpha to beta. And alpha and beta are what? Like, what are alpha and beta? Like, we talked about this earlier. Like, if you look at, like, this stuff up here for that integration formula, what are alpha and beta? Like, practically speaking. Oh, Roger, yeah. Yeah, so almost what I want to hear, it's like right here and right here, because you're going to want to integrate from theta equals alpha to theta equals beta. You're interested in the stuff angularly between those two. You're going to go from theta equals alpha over to theta equals beta, but like you gave us now the practical procedure for figuring that out. How are we going to figure out what alpha and beta are? Oh, you just need to find the intersection of those two curves. So we need to know, hey, when is 6 sine theta equal to 2 plus 2 sine theta? Right, because that will give you the intersection of those two curves. Let's subtract 2 sine theta. You get 4 sine theta equals 2. Let's divide both sides by 4. We need sine theta equal to 1/2. Oh, thank God, that's actually not that hard to solve. So what's my alpha going to be? We get two solutions, given the fact that we know we're in quadrant 1 and quadrant 2. So what's like the solution for sine equals half in quadrant 1? See if people remember. Do you remember? Okay, I'm just gonna say it. It's 30 degrees, also known as pi over 6. So this alpha right here is pi over 6. And then over here, notice they're gonna have the same reference angle. So this one's gonna be 5 pi over 6. Cool. So we can now set this up. Do you remember from 101b, if you have two curves, F and G, and you want to find this region here, and the points of intersection are A and B, what do you need to do to find that region there? Not necessarily. You could just do this. That's if you wanted to rotate it. Does that make sense? Yeah. So we're going to do the same thing here. We are going to integrate from pi over 6 to 5 pi over 6. And what is our top curve here? Because we're going to do, like, remember how, like, this over here on the, for rectangular, we're going to do F minus G. So what's my top curve in my example I'm doing here? Switch it, yeah, the circle, cool. So I'm going to do 6 sine theta. Now, can I just put 6 sine theta here? When we're finding the area with the polar, what's the formula actually say you have to do? So I'm scrolling up so you can see it. Yeah, you're gonna have to square it, and we're also missing something else. Yeah. So we're gonna have half, and then all of this is gonna be squared d theta. And then I'm going to have to do the same thing, minus integral pi over 6, 5 pi over 6, half, and then this one is 2 plus 2 sine theta quantity squared d theta. We can forget about the halves for now, but there it is. Okay, so does everyone see I'm just using the formula? Basically, the area we want is the area of the circle minus the area of the cardioid. Okay. Oh man, so this is gonna be like a lot of work. Damn. I'm like not looking forward to integrating this, but let's do it. Woo! Okay, so let's first of all let's just let's square and see what we get. Okay. 1/2 pi over 6, 5 pi over 6, 36 sine squared theta d theta minus half integral pi over 6, 5 pi over 6, 4 plus oh my god, 8 sine theta plus sine squared theta d theta. Technically, I should put like the little, there we go, cool. I guess you really don't need it. Let's get rid of that. That just makes it look ugly. Cool. Boom. Okay. So, damn. Ooh. We're gonna have to do some changes here. I'm just gonna look at the book because I don't want to have to like think about this off the top of my head. Apparently, the way to solve this problem, because I haven't done like trigonometric integrals for a long time. So first of all, let's just take out that 36. And half of 36 is 18. That makes sense. Okay, so sine squared theta. Does everyone remember the half angle identities? Or, sorry, double angle identities? Apparently that's what you would do here. Actually, I do remember that. The double angle formulas, and it's called the power reduction formula is what you would do here. The sine squared becomes 1 minus cosine 2 theta. I do remember that. Okay, so for the other one, we're going to split that up and we get like a bunch of little integrals. We'll just distribute in the half. So when you distribute in the half, you get 2 plus 4 sine theta. Okay. Wait, did I distribute the half in right? 1 second. Yes, okay, so plus half sine squared theta d theta. Boom. Okay. And you're going to want to, actually let's do this right now. You're going to want to use the same power reduction formula. So let's change that for that sine theta, sine squared theta. Okay, and at this point, you can actually find the antiderivatives of all of these. You can definitely find the antiderivative of 2, you can definitely find the antiderivative of this one, and then I'm just gonna, if you look up in your book, it's not hard to find these. Does it make sense? I'm just gonna skip over to what the number is, because I feel like it's sort of a waste of our time to go through all the steps. Does that sort of make sense? You can see the antiderivative for that in, what's it called? If you look in a table of derivatives. So you end up, because what we care about is the fact of like how we set this up. You end up getting 4 pi for all of this after some canceling. What I'm really concerned about here is the setup and understanding the picture we've got here and the use of that. And I don't want to like spend like another like 10 minutes simplifying all this. Sorry. Okay, yeah, that's actually a really good question. It will depend, and sometimes I will specify. Like, sometimes I will say, please do show me all of the steps. Okay, now for something where I ask you to show you all the steps, I don't think I would give you something this nasty. Does that make sense? Especially the one where you're gonna have to, like like remember, like basically remember, or actually, yeah. So I would tell you, like sometimes I would and sometimes I won't. Usually, first a lot of questions, like sometimes I'll even say like, can you please set it up, and then solve with Wolfram. Or sometimes I'll say I've set it up for you, and I want you to show me all the integral steps. So it would completely depend. Does that sort of answer your question there? But a lot of the time I give you the option to set it up, do some of the calculation yourself, and then when you get to a certain point where you're like, I would not be upset most of the time if you were like, then at this point like, okay, and then you would have something like, I looked up the table of integrals, and let's just fill that in to give you an example. Let's see if we can find in the table of integrals like the power trig integrals, trigonometric integrals. Because I think this one's in there. Does anyone happen to remember what the name of this formula was? Like the 1 minus cosine 2 theta over 2. There's a formula for that trig substitution. Does anyone remember what it's called? That was 101B, end of 101B material. I can't remember the name. It's like not coming to me off the top of my head, like what that will end up being. Let's look it up. Power reduction formula. This is what's cool about the internet. You can find so much stuff. Let's see. Okay, that is the power reduction formula, but I don't see the integral for it. One second while I peruse the internet. Let's just say I will definitely most of the time allow you to do that. I can't remember how to solve this off the top of my head. I haven't done, what's it called? Trig substitutions for a long time, so I can't remember the steps myself, which is sort of funny. But do you get what I'm saying though? That if I want you to show most of the steps, I'm not gonna. I see my goal for this class most of the time, because like, let me like rewind a little. Who here is gonna take like a physics course? Like say, get me in the chat if you plan on taking like having to take a bunch of physics or something for your major. Okay. Cool. Well, there's some. Okay, good. There's a good number of you. The hard part with physics usually is understanding how to do the setup right here. Like a lot of physics problems, they're just like applied mathematical problems, and the thing where most people mess up is the setup. Because in a physics class, like most of the time, like you once you have the setup and you get the answer, like using either Wolfram or like plugging it into a calculator somewhere, that's what you're going to care about. And what they care about is seeing the setup. And I'm sort of taking the same approach here. When I set things up, I'm not going to be too anal about like the actual integration, because I care a lot more about you explaining and like drawing the picture and like what I was doing. Like, what we're doing here is, we're integrating from some angle to some angle of this region and the setup. Okay, so like, so does that basically answer that? Okay, cool. So like we got to a point where it's like we split it all apart, and then this would be solved. Sometimes integrating is important. Today I'm not really feeling it, and then a lot of the time that's not going to be the focus of what I'm going for. So let's just say that. Cool. Okay, what time do we go till? Okay, cool. So we have like 10-ish minutes. Okay. Let's keep going forward. Ooh, okay. So we've talked about finding area with integrals for polar coordinates. Let's now talk about finding arc length in polar coordinates. Let's change the heading. Whoa, what was that? Okay. So let's sort of spend a little bit of time deriving the formula. Okay, so do you remember for rectangular coordinates, you had a nice formula. It was the integral from a to b, the square root of the derivative of x, derivative t, quantity squared, plus derivative of y, derivative t. This was for the parametric equations, remember, but they're in polar, rectangular coordinates, dt. Okay, so we're going to start with this, and we're going to see, like, well, what do you need to do to get them in polar coordinates? So we're going to make some changes here. So remember, your f function inputs a theta, and it spits out an r. And your theta goes between alpha and beta. Okay, and we have our little formulas that we can use to change things around. So remember how x is equal to r cosine theta? And we can make a replacement here. What is that r equal to? So this r, what is it equal to? There's like a particular function that always gives you the r value when we're dealing in polar coordinates. It's f, right? R equals f of theta. Okay, boom. So likewise, y is always equal to r sine of theta. So the y value is equal to f of theta sine theta. Okay? And in the arc length formula, we don't care about x, we don't care about y, we care about their derivatives. So we need to calculate that. So x prime is equal to, we're going to have to use the, what formula are we going to have to use to take the derivative of this? Or what derivative rule are we going to have to use? Yeah, product rule, cool. So we're going to need f prime theta cosine theta plus f of theta minus sine, so let's erase that. So this is going to become minus f of theta sine theta. Okay, likewise, we'll do the same thing for y. Y prime is f prime theta sine theta plus f of theta cosine theta. Okay. So now we can start transforming the rectangular equation. So the rectangular integral went from a to b, square root dx dt. And actually what you could call these up here is that this x prime is dx d theta. right? Because you're taking x and you're taking the derivative with respect to theta. Likewise, for this y prime, you can call it dy d theta. So to keep going with this, I'm not going to put the parentheses around it. Okay. So you can make these replacements. The dx dt squared is now dx d theta squared. The dy dt is dy d theta squared. Okay, and because you're changing from the independent variable of t to independent variable of theta, this is now d theta. And our t variable, remember, used to go from a to b, and that's where the bounds of integration came from. Now that your independent variable is theta, it's going to go from alpha to beta. Okay, so we've changed. We went from the t variable to the theta variable. Okay. And let's keep plugging this stuff in. So now you're from alpha to beta, square root. Okay, dx d theta, we had already calculated that, so let's put parentheses around it. You're going to have f prime theta cosine theta minus f of theta sine theta quantity squared plus, okay, now you have to do the same thing for dy d theta. You're going to get f prime sine theta plus f theta cosine theta quantity squared d theta. Okay, now I know that this looks really ugly and really bad. You're looking at this, you're like, oh my god, this is like a horrible formula, but actually it's gonna simplify and become pretty good. So let's go through and look at what's gonna happen with this. Okay, so let's do the simplifying. Okay. Oof. Okay, working myself up to it. We only have a couple minutes left, but we can do this. Okay, so let's go through and multiply it. So I'm gonna only work on the inside part right now. We'll forget about the fact that we're integrating. So we're gonna have f prime theta squared cosine squared theta minus 2 f prime theta cosine theta. So we're going to do this one here, right here first, the one on the left. So 2 f prime theta cosine theta f theta sine theta plus f theta squared sine squared theta. Okay, I think I did not make any mistakes on that. Okay, now what about the other one? The one on the right. So on the next line, we're going to have f prime theta squared sine squared theta plus 2f prime theta sine theta f theta cosine theta plus f theta squared cosine squared theta. Whew! Okay. That's not too bad. So let's put like a big plus between them. Okay, there are some terms that you could gather. What terms can I gather? Like, it's actually pretty cool. I think they're basically lined up, right? Do you see how, like, these two right here, they have an f prime squared that you can factor out? These two over here have an f squared that you can factor out. And then over here, these have a f prime f that you can factor out. Okay, so we're gonna do that. So looking at, let's factor out the f prime theta squared. Okay, so you factor that out, and then you're left with a, this is pretty cool, cosine squared theta plus sine squared theta. So what's going to happen to that? That just becomes 1. You're like, oh, thank God. Ah, yes, not too bad. Okay, so that goes away. And then let's see what else we got here. You factor out, you could factor out your f theta. Actually, no, let's do the middle one first. Let's just leave it as, we'll factor out our 2 f prime f, and that leaves you with a, oh, actually, oh my God, no, it's not that they factor out. What actually happens with those? Let's see if you guys can see it. If you look at those two middle terms, what happens? Yeah, they cancel. Thank God, because you have that minus and the plus. Okay, which means you factor out f theta quantity squared, and that leaves you with a cosine squared, sine squared, and you're like, oh, this is awesome. It goes away. Oh, so you're like, thank God. Okay, so you keep going. And you're like, yay, this becomes an integral alpha, beta, and you're left with square root, and both of these are squared. So you get f prime theta squared plus f of theta squared d theta. And one of these can actually become something. Which one is it? So one of these can be rewritten as a particular variable. So like this is like almost our final form, but like we can do some like rewriting. So one of these, f or f prime, is equal to a variable. Which one? Let's see if we remember. No, it's f of theta. What is f of theta equal to if you scroll back up? Yeah, it's r. F of theta is r, which means f prime is dr d theta. So what you can rewrite this as is the square root of the f theta is r squared, and f prime is dr d theta squared. D theta. So either of these, we can call this form 1 and form 2, depending upon if you're using the variable r or if you know what f is. But either way, they're equivalent to each other. And that's where we're going to end for today. We'll do an example with this next time. Yeah, it got cut off. It's supposed to go. Yeah, it's supposed to be like that. Cool. So before you leave, please write, I was here. We're done. And I will see you tomorrow.